Thanks, Norga, and thanks, everyone. Okay, so the big title. I want to talk about our revolution, of course. So just so you know my standards, these are my standards for scientific revolutions. In each of them, this intellectual revolution that started with an idea, the idea of proofs, or the idea that disease is propagated by microorganisms, or the idea of natural selection, or the idea of curved time space, or the idea of computation. And each of them fundamentally change math or yes. I have lots of jokes, but that's serious. So yeah, so I'll tell you from this viewpoint, I want to talk about our evolution, the theory of computation revolution, and then that will be half an hour. It will be very quick, and then I'll talk about NP and PCP revolution within it, as demonstrating lots of the ideas that you'll see in the first half. So like Noga said, I don't know, he predicts everything. This is my view. So the theory of computation stands in the center, in the intellectual center of math, of computer science, and essentially of all sciences. And I want to explain this or demonstrate this, but you know, like even I, with my limited PowerPoint skills, can generate such a picture. You can equally put in the center. Yeah, so this is my, I want to convince you of this. Everybody can put in the center of the world whatever they like. So, and in fact, putting in the center whatever you like is not a new tradition. It's a very old tradition. You may remember the geocentric. This lasted about 1,500 years till it was revised by another scientific revolution. You know, it's not just an old tradition, it's a new tradition to put in the center. So anyway, this is the one I'll focus on. I want to talk just very briefly about how, or in what sense, is the theory of computation part of the technology side, part of the mathematical side, and part of the scientific side of the intellectual sphere. And before I move into the NP and PCP story from my viewpoint, Guy told you it will be somewhat similar and somewhat different. So the birth of the field is really, you know, can be pinpointed, even though, of course, there are lots of work before and after, to this amazing paper of Turing, where he introduced the first formal definition of a computer, of an algorithm. And you may remember, especially those of you who are graduate students, that he was a graduate student at the time. And this is the kind of thesis you'd like to have. Well, it's both the seed of the computer revolution, that's the impact on technology. It's the origins of the connections to computation and the sciences through the Church-Turing thesis. And the fact that it's formal means you can prove theorems here. And we'll talk about these three aspects in the first half hour. So what's amazing about this, maybe everything with hindsight looks obvious, and is that the model that Turing proposed was both local and simple. Operations are local and simple. And the first thing it suggested is it can be implemented. You know, it just can be implemented with very simple gadgets. And not only can it be implemented, he went immediately to implement them, and others did as well. And that gave birth to the computer revolution. And I think for theory of computation, it's absolutely essential that we have this technological field evolving, generic field technological, which keeps suggesting new technology, new systems, new requirements from users, which feeds theory and demands new models, new algorithms, new limits on these models, and so on. But what I want to stress is this goes no less and even more the other way. Of course, Turing's paper is the best demonstration because there was theory before practice. And I'll give you a few more examples. And for this, I can just start from the many theories that were developed in the theory of computation throughout the years since Turing's time. I'm not going to read them, and you know many of them, but I'll just focus on some. And I want to say that in many, what I want to suggest in this half hour of the talk, many of you know some of these, maybe many of you teach some of them. And I think some of the things about them are not stressed enough, specifically the power of theory, especially because the power of technology is so evident to everybody that, that lives today. So I'll focus on some. Let me say that, of course, they are all, despite the fact that many were developed as theories, they are obviously practical. We see them every day, and I want to focus on a few aspects. So if we look, for example, at algorithms, I'm always reminded of when I was in elementary school and then in high school, we learned about heroes of invention. And we had these riddles or sometimes exams about what did X invent, the Hall of Fame. And I don't even know if all of you know all of these. I don't know if that's popular anymore. But that's very famous inventions. And what I think is not clear to any high school student today is you can ask the same question about these people, and I'm not sure who knows the answer, and I'm sure that all of them have to know the answers because they live it. So of course we know, I mean, at least computer science knows that what these guys invented, and they invented algorithms. And what is not clear, maybe, is that these algorithms are absolutely key to the generation of huge industries. So I don't know how much of this is taught when you students or students among you learn algorithms courses, but in all of these cases, there was an algorithm that was sort of trivial, and all these guys improved it by a linear factor. Just a linear factor. And what it's created is, change the world again and again, in navigation, in signal processing, media and communication, in biology, in internet search. And I don't know how many of you know that know this algorithm, but you know that there are all algorithms to do things that are very natural. The first is dynamic programming. This is basically recursion. This is interpolation. This is basically, well, not sure I can summarize. Eigenvalue computation, gradient computation. Improving this efficiency by a little bit created billion-dollar industries. If we focus instead on cryptography, I want to say that each one of the theories is actually lots of theories in itself, and there you can just count the number of revolutions that happen within this field. It is theories, many theories that every new years create more applications and more, basically more industry. And they connect to everything in other areas of theory of computation. In fact, that will be one of the main points I want to stress, the interconnectivity of the field. But again, this is not just practical. In most of these cases, and especially the beginning, the early 80s of this, or late 70s and early 80s of this field, this completely predated application. It was only because this theory existed, because of the availability of security of privacy, that the internet could develop without any investment by governments. It's just private people recognizing the value, the potential value of having a secure internet. And you can focus further on things like, so one key insight there is not only easy problems or efficiency is useful, also having something we cannot solve is useful. This is a major insight of the field. This is a revolutionary insight. If we focus further on my favorite zero-knowledge thing that will come up again, I want to say something that's was not clear then, and it's much more evident now. That it appears in other contexts that we didn't expect. Child education, nuclear disarmament, anonymous DNA testing. I'm not elaborate. You should find out more. I used to give talks in the 80s and the 90s, and it always started, this will never be implemented. This was too complex to be implemented, because that's what I heard from my friends who were doing practice. But, you know, here is a list of companies by all my friends, Eli here, and Shafi Goldwasser, and a different one by Silvio Micali. You know, they are making money of this fact that it can be implemented. And it appears, zero knowledge, in explaining paradoxes in quantum mechanics. It appears in places that we didn't expect. So not only these theories are valuable for what they were sent out to be, but in completely different contexts. And in PCPs, and we'll see. We can look at quantum. Anyway, I'll rush through it because, you know, we were again playing games intellectually for about 2 decades. And then, mainly because of Shor's algorithm, the world began to invest in it, began to invest billions in it. And it raises a question of whether actually these machines can be built. Is this a realistic computational model? And it raises challenges to physics itself, whether it's actually a feasible theory, a complete theory. Maybe it has to be revised in the large scale. And it creates basic scientific, both questions and answers that have to do with, for example, testing scientific theories. And interactive proofs will play a fundamental role here, as we'll see. This was just the connection to technology. Connection to science, I'll be very brief and rush through it. What is there about Turing's model that makes it so you know, universal? Well, we know it's you know, the computation. If you just look at what the machine does, it's an evolution of you know, it's an evolution process of simple and local steps. But after many steps, you know, you can do complex things. And when we think of it, usually, or when we used to think of it, the simple things were bits in computers, or maybe a little later, computers in big networks. It was technological. But the same applies equally well to neurons in the brain, to cells in you know, living tissue, to prices in markets, to bacteria and petri dish, and all these other friends in Facebook. It's the same. And given that, you know, you can view all of these things and information processes and analyze them like we analyze computation with the same tools. This was, of course, realized already by the founding fathers, by Turing and by von Neumann in their works, Turing on morphogenesis and on intelligence, by von Neumann on the brain and on self-replicating automata. And I would say that the one thing that over the decades has evolved, and we do it now sort of matter of course, this methodology that we developed in which we model and develop algorithms, study resources, and strive for efficiency, prove upper and lower bounds, and do reductions and completeness and abstraction and play, which is a very important aspect. This we can propagate. And I want to stress this play, you know, in understanding something like bacteria and petri, or maybe understanding computers in a network. It may be essential to study quantum bacteria, maybe in hyperbolic petri dishes, which are not quite, you know, realistic. I'm not suggesting it, but I wouldn't be surprised if this turns out essential, as you know, given what you'll see later. And so what we bring to science with this method, you know, is lots of things, questions, the definitions, principles. You can read all that, and it starts to take. You know, the connections are increasing all the time. I want to stress that unlike computer technology, this will take longer. Sciences are very conservative, and as we know from many examples in the past, many of the, in fact, scientific revolutions took decades or centuries to be accepted because of the conservatism. But it will happen. I want to say that the NP completeness we'll talk about was one of the early successes of, you know, an export from theory of computation to the sciences, because scientists prove NP completeness results. Thousands of them. There must be something universal in this notion, in fact, in computation itself, that drives that. And so connections between the theory of computation and all the sciences, biology, economics, physics, and many others are growing, especially in the last couple of decades. And if you want to read more, there is a free book online that you can look at. It has other things. In particular, it says something about the field. I mean, if we are servicing so many much larger fields, the field of the theory of computation must grow. That's something we have to realize, and I'll talk about this at the end. I want to finish this set of connections with a connection to math. And this will be very important because the theory of computation is a mathematical discipline. And that started, again, by the fact that Turing's model was a formal model. There's a very formal definition of what a basic step on a computer is, or what a basic memory unit is. And using that, you can start analyzing algorithms or prove limits of them, in short, prove theorems. And in fact, again, Turing was the first, and in his paper, he already said that computers cannot do everything you might think, or cannot do everything as the people outside believe, right? Cannot solve the halting problem, cannot test whether a theorem is provable in some formal system. And while it started from logic, and initially this connection was very strong for 30 years till the 60s, it became mainly a user of tools for mathematics, especially discrete mathematics. But quickly, after borrowing some, more and more tools from more and more areas, it began to contribute back. So by now, there are lots of collaborations and interactions. And in fact, we are proving things that are completely mathematical that may have nothing to do with computation, like parametric inequalities or metric embeddings or explicit construction, so on. So in ToC, for example. So we both generate lots of questions. There are lots of collaborations. And it happens with more and more areas of math. Is this practical? Who cares? This is an essential part of our field. To develop, to solve our essential problems, we need to do that as well. What does what? I can tell you later. So it's about first-order logic, proving that some structures, some sentences are undefinable. I have, here is the second one is here. First order, that's, for example, and the third from the bottom. So in particular, these collaborations have solved major open problems in mathematics. I'm not going to read them all. You know about some of them. I want to stress that many of them were open a very long time. And this is something we have to accept. Being in a field where technology breathes down our backs and wants to see application, we have to remember some of these things, and we'll see that soon again. Some of these things take time. And it's not just the theorems, the major theorems that are proven. Some of the major open problems of mathematics are open for a long time and are about computation, directly or indirectly. For example, from the 7 clay millennium problems, which some of you know of, where you can solve one and get $1 million, the Riemann hypothesis is really a question about pseudo-random walks, if you look at it right. The Navier-Stokes equation, through the ingenuity of Terry Tao, is really about the Turing universality of water. And you can read about this in Terry's blog. And of course, there's another one of the 7 that's clearly about computation. And I want to talk about, this is a good segue for me to continue to the second half of the talk. So we are deeply entrenched in mathematics, and we are doing mathematics while, having these implications or interactions with technology and with the sciences. So I want to start with something you all know, and this will be my proof 1.0. I said that I'll talk about connections to proofs and to Euclid as guided. The big mystery after Turing's result of undecidability was not about whether something is computable or not, but how long does it take? Which problems are hard? Which problems are easy? And what's about this brute force search? Is it really essential for lots of problems? So we had, we knew lots of problems we can easily solve. Two coloring, two sort, so on, multiplication. We call this class P. And there were lots of problems that looked extremely similar to them. It changed a little bit one parameter, and it looks much harder, for which, the only solution, the only algorithm we had was just trying everything with 2 to the n time. And, is it real? Is it imaginary, this difference? And a major insight, again, of the field is that something is common to all the problems on the board. And this commonality, again, it's really a major insight, is that in all of them, all these problems, solutions can be efficiently verified. This is NP. Put differently in a mathematical way, these are theorems whose proofs can be efficiently verified. Now, when you say can be and can be, it's really, these are the only ones we care about. We essentially never care about solutions that about problems where we won't recognize a good solution if you show me one. We don't care about theorems if when you show me a proof, I don't understand. We don't care about them. So these are the only things we care about. So this brought the P versus NP to the fore, and we needed to resolve it. We have to understand it, but we still don't know. So what do we do? Well, at least if we don't know, we can compare two things we don't know and prove theorems like if 3 coloring is easy, then factoring is easy, or 3 sort is easy. Which again, we forget it and we teach it sort of in a maybe already bored way because we understand it. It's a fundamental connection between things that look completely different, completely different. We know how we do it. In fact, we know this connection is stronger. Some problems capture the complexity of the whole class NP, of everything we don't understand. These gadget reductions we understand, again, to boredom, and it critically uses the locality. Again, locality plays a major role, can convert a formula to a graph where satisfying assignment will translate to a legal coloring, and where we can read off the truth value from the colors. And the fact that computation is encoded in so many structures fits back to the Church-Turing thesis and to mathematics. So we couldn't solve the P versus NP problem. We said, OK, let's just assume it's different. Take it as a proxy for hardness. And we know today thousands of problems that are NP hard all over science. If one is easy, all are. If one is hard, all are. And this is a universal phenomenon. It's everywhere. Why do people prove NP completeness results or even think that way? In every field, it captures something else. For programmers or computer scientists, it's a certificate for computational hardness. In mathematics, maybe for structural nastiness. And in science, it's basically whether your model, if your model of nature solves an NP-complete problem, something must be wrong. Okay? You have to think what is wrong. Maybe instances are special. Maybe your model should be revised. But you can think of P different than NP as a law of nature in the same sense that the second law of thermodynamics is. It's a guide. And in fact, complexity, computational complexity, is and becoming a guide in science. And that was the situation. We already accepted NP hardness as a proxy for, since we don't know it's proxy for hardness, but it didn't explain everything because, after all, and here I'm moving to the second generation or third generation of proofs. If we can't solve something optimally, we can try to solve it, suboptimally. So we knew essentially that everything we want to solve is either in P or NP complete, but these hard problems, NP complete problems don't go away. Let's settle for approximation. So how well can we approximate the optimum? People started developing approximation algorithms, and they discovered that for different ones, you get a different number or different function, at least in their algorithms. And the mystery became much more complex. It's not P or NP complete. There seem to be, different problems are different. So what can you say? Well, are these the best possible? Can you improve them? Have a theory for that. And the theory for that I want to talk about took 30 years to achieve, from NP completeness to, let's say, Hastad's result, that 3 sat is 7/8 to approximate. Took 30 years. So what happened in these 30 years? If you look at this, 30 years, what happened is sort of, I don't know how many of you know this book, children's book, where, I mean, it's roughly like these stories. It's how the elephant got its long trunk. It's basically in this story is that, you know, it was coming to drink some water, and, well, it used to have a short nose. The alligator caught its nose, and, yeah, blah, blah. That's how, yeah, I mean, that's roughly as believable as this story. So I want to tell you this story. So the story, in fact, let me divide it so I have stepping stone. The middle one is the PCP theorem, if you recognize it. This took 1 decade. This took about 2 decades. And I'll tell you about each. And what needed to happen, and I want to stress again, things had to happen in different universes for this progress to make. So it's not like time passed and nothing happened. It happened a lot, but maybe in a different neighborhood of ToC. So in this decade, I mean, of course, I'm oversimplifying by just giving you a hint of some of the things that happened that were needed for this step between the PCP theorem and Hastad's optimal inapproximability result. And some of them are here. Somehow you had to study influences in Boolean functions. And the motivation for that was understanding both distributed systems and questions in game theory. And tools for that had to come from mathematics in the form of Fourier analysis and other concentration inequalities like hypercontractive and so on. So I want to, I'll give small detours into these yellow blurbs throughout the continuation, the last part of the talk. And here let me tell you about influences, just in case you haven't seen them. What are influences in Boolean functions? And maybe understand something that Dor hinted to in his talk. It's a completely different question raised by Benor and Lineal. It says, you want to do voting or you want to jointly flip a coin, n people. They each flip a coin, and then you want to combine them. Which function is the best to use when you combine them so that every player has the smallest influence on the outcome? Let's say this bad player votes last. What function would you use? Well, you can try several functions you use, like parity. Let's do a table of what the influence of this player is. Clearly, if this player votes last, he can set the function at will to either 0 or 1 after the others have voted. So that's the worst possible function. Every player has total influence. Okay, say, well, of course not. We'll use majority. That's what we use in voting. And you see, in 9 players, you get about 1/7, which is not quite 1/9. It's not bad, but say, well, maybe there are other functions. And in fact, there are other functions. Majority of majorities seem to do better. It's 1/8, but it's not quite that. And you see when it scales with n, it doesn't scale that well. And there's this amazing theorem of Kahn-Kalai and Lineal that we keep using and variants of this, saying that it's impossible to have a function where every player has proportional influence. For every function, there will always be a player with unproportional influence, log n over n. This, and the proof of this, are key to this development with optimal inapproximability. So that's an example. Let's talk about the first 2 decades, and this will take me longer. So we knew 3-SAT is hard, and we want to say that 3-SAT is hard to approximate somewhat, it's 0.99%. The story here, and I'll elaborate, was a story of proof systems, of the many variants and evolution of proof systems. IP, 2IP, or MIP, PCP. And the way they came about, I mean, you think they are natural. They are natural. They are extremely natural. With hindsight, you don't need anything to define them. But that's not how they came about. IP was defined because of cryptography. And MIP was defined because of zero knowledge, as I'll show you. And understanding them required, again, development of arithmetization, so I'll talk more about this. And then, only then, could we determine the power of these classes, exactly determining complexity settings. And then was the connection made to approximation. And only then it became essential to understand precisely what the power of PCP is. And then it was clear that this is equivalent to the statement about 3 sats. So let me tell you about this story in 5 minutes instead of 1 minute or 7 minutes. I want to stress that zero knowledge was not only there in the beginning. The PCP theorem also turned out to be essential for zero knowledge. So the interconnectivity here is sort of, I would say, well, I don't know. I've been 40 years in this business, and I keep being surprised by connections like this. That was Barak's result. So again, stressing this point. So I want to talk about this revolution of proof. We talked about proofs since Euclid time, defining mathematics. We talked about the notion of proof as, having to be essential for any theorem we practically care about. And these were the usual proofs till the late 80s. So I want to tell you about IP. So let's again recap what NP is. NP is a standard written proof. Weil thinks for 7 years about Fermat, and then he writes a paper and sends it to a referee, and the referee reads it. That's NP. These are standard classical proofs. In IP, you allow, what the Greeks liked, a discussion or dialogue or an interrogation by a student of a prover. And there you decide to accept an input to the language if the conversation convinces you with high probability. And of course, you make sure that if it's not a theorem, or if X is not in the language, you reject it with high probability. So that's interactive proofs. In fact, Babai was motivated by questions in group theory, and Goldwasser, Mikali, and Rakov were interested in cryptography. And in fact, the cryptographic aspect was in order to not just have different kinds of proof. Why would you do that? Of course, it's a natural extension, like randomized algorithms extend deterministic algorithms. These are probabilistic proofs, interactive probabilistic proofs extending normal proofs. That was not the point. The point is these kind of proofs have extra properties that cannot be expected from written proofs. And in particular, one of them is a zero-knowledge property, where you want the same, you want it to be a convincing proof, but you also want that the other side doesn't get any information. And this seems to be completely ridiculous and impossible. Intuition is wrong. And in fact, with cryptography, assuming one-way functions, you can show that not only it's wrong, but in fact, every theorem which has a proof has a zero-knowledge proof. It's a major consequence to cryptography. So every theorem that has a proof can be proven in zero knowledge. You can just transform it into a zero knowledge proof in this model. And then once you have this and once you realize this, you start worrying about the assumptions. And do we need cryptography here? What do we need? Well, it turns out that in this setting, in a one-prover setting, we prove that this is equivalent to having one-way function. So there's nothing more you can do. So how can you remove assumptions here? And while this is a joint paper, I can tell you that while we were querying this, Shafi, with an incredibly fertile mind, said, why don't we try two provers? And, why not? Well, two provers, these are the two prisoners in the prison, where the police interrogates two people who cannot talk to each other. That brings a lot of credibility if they are consistent. So again, the definition is the same. A verifier accepts, an efficient verifier accepts if the conversation with both of them, this happens exactly when X is in the language with high probability. And in this model, so just two provers instead of one, you don't need cryptography. You just don't need. You can prove everything in zero knowledge without any assumptions. That was our motivation. But, one motivation is created the model, and then the model had life of its own. What is the power not only of IP, what's the power of many IP? And for a while, You know, what's the power of randomness and interaction in proofs? This was an open problem. And complexity looked at it for a while and just didn't know. I mean, there were obvious inclusions, and there were a few examples of things that seemed to be slightly outside of NP. And that's all we knew for a few years. And for things to change again, things have to happen in a completely different universe. And this is a universe of program checking. Started by Blum, Blum-Canal, Blum-Luby, Rubinfeld, and then later Beaver, Feigenbaum, Lipton, Noam Nissan, and so on. Here's the problem. I give you a program, you buy a program for computing P, computing a function G. Compute G of X. Well, what do? You run P on X and you get there. But suppose the program, you know, errs on 1% of the input. You don't know which. Maybe it errs on X, maybe it doesn't. What do you do? It's a very general problem, and the fact that there are sensible answers, not just sensible, in fact, I'm summarizing a theory here in a sentence. This can be done in great generality for a vast amount of programs. And because of that, in fact, the way it happens has impact on lots of things in complexity. Guy talked about it. Has to do with arithmetization of Boolean functions. It impacts hardness amplification, local testing and decoding of codes, property testing, sublinear algorithms, many other things were generated from it. But this has to happen. This random self-reducibility of programs had to happen before we understood the power of this interactive proof set. And then within a few weeks, as Guy told you in the morning, I'm repeating it, or maybe a couple of months, these amazing developments happened where Noam Nissan showed a two-prover interactive proof for the permanent, then a one-prover interactive proof for the permanent, then IP equals P-space, then MIP equal next. And the complete understanding of the power of these interactive proofs in classical complexity terms. And once the last result was understood and scaled down to NP, we had this amazing, only then did this amazing connection happen to approximability or to inapproximability, that we can use these results or these interactive proofs as means of hardness proofs for approximation. And then it was critical to get all the parameters right and get, in particular, the PCP theorem characterizing PCPs. And here are the PCPs, which I didn't define yet. It's exactly the same, back to normal proofs, written proofs which you send to a referee. Only this is the NP version. In the PCP version, this referee is the referee you would like to be. You don't need to read the 100 pages. You read 3 bits in the proof, you evaluate some function, and decide whether to accept or reject the paper. That's the ultimate referee. And the fact that this is possible for any proof, but it can be done for all proofs, right? It's sort of stunning. Stunning for math, stunning for theory of computation. And this is a theorem we know, NP equals PCP. And if one wants to complain, and Israelis like to complain, is that it's very hard to teach. It's very hard to teach. It's very sophisticated. And of course, I'm not going to say anything about it. But it's clear that it would be nice to simplify the proof. And it was a lot of work that was invested. And it was greatly simplified. But more was done than just simplification of proofs. Irit Dinu came up with a completely different proof. This is algebraic, and Irit's proof is combinatorial. It happens by gap amplification. So somehow this is a gradual process which converts a unsatisfiable formula to one that's hard to approximate gradually in combinatorial fashion. And for this, something else has to happen elsewhere in a completely different world of space complexity, Omer Reingold's result. SL equals L, or undirected connectivities in logarithmic space. What does it have to do with PCPs? This is a problem for those of you who don't know. I mean, the problem of SL equals L is a problem of navigation in unknown terrains. This is a very old problem, and it's a very new problem. we always knew you want to navigate an n-node graph without any memory. You just can remember where you are. And it was known that this can be done randomly. It's an old result from the 80s. What you expect is maybe what you expect. It's not true in directed graphs, but in undirected graphs. You just walk randomly. You will eventually cover the whole graph efficiently with high probability. And the question was, the question we like in theory, I give you a probabilistic algorithm, get rid of randomness, make it deterministic without changing other resources. And it took many years, 25 years. As usual, something had to happen for that too. I'll tell you in a second. But Omer Reingold came up with a deterministic work and solved this problem. And so what does it have to do with the Nurse PCP proof for the combinatorial proof with the PCP theorem? Well, I'm just going to show you a picture to see why it's similar. These are on the right you have Reingold's proof, on the left you have the Nurse proof, and you see that the same thing happens. Only on the right-hand side, it happens to the eigenvalue of the graph. In the left hand, it happens to the inapproximability of the Sutton sets. Of course, she has to prove everything for scratch. It's a different theorem, but it's totally inspired by this. And there's a strong connection. So, what happened? How did Omer get to his result after 25 years? Well, a lot had to happen in the expander world. So it's, again, a completely different universe, which have been studied for decades in the theory of computation. In particular, what he needed is the zigzag proof, which Omer and I developed with Khalil Vadan. But expander graphs, well, let me get to the next slide, is something we've been studying throughout, and somehow, without motivation, clearly is extremely basic and turned out to be useful. In fact, there's no area of computer science, of both practical and theoretical, that is not impacted by the existence of expanders. Really, without expanders, you can't go anywhere. Of course, you saw in Doe's talk that it's essential. And in particular, not just expanders, but the explicit construction of expanders. And this is one area where our connections with mathematics span very, there are many connections to many fields. Explicit constructions come from group theory, they come from algebraic geometry, they come from number theory, different ones, and different connections. And the zigzag one happens to be a combinatorial proof of expansion, explicit construction of expanders. And again, this has life of its own, and there are many extensions of expanders. And studies of small set expansion had to do with algorithms for unit gains mentioned earlier. Expanders were, by mathematicians, were raised to higher dimension, higher expanding complexes. We'll hear later in this conference from Irit and others about high-dimensional complexes expanding connections to local testing. And this, even though the Grassmann graphs that Dor mentioned would have been natural to consider maybe without any motivation, seem to have arisen naturally from the study of high-dimensional expanders. There are ways in which things happen that maybe they have to happen this way. Okay, so let me, in the last 10 minutes, tell you about the last 2 decades. So we had the PCP theorem, and what happened in the previous decade. So we could prove some inapproximability results. We knew exact, inapproximability for 3SAT, for 3XOR, for set cover, and many others. But, what are these numbers? What's the reason for these numbers? Where are they coming from? And it took about a decade to understand. Hot formulated this unique games conjecture, which I'm not going to define formally, but it's basically the inapproximability of a very basic problem of linear equations, whether you can distinguish them, whether at least 1 minus epsilon of them are satisfiable, or at most epsilon. I want to stress that this is a kind of thing that should be shocking for mathematicians at all that anybody would consider linear equations as a serious problem. Clearly, it's an easy one that we got rid of in the Gauss times. No. Understanding it when you allow error or approximation becomes a major problem. And he proposed it, and then there was a decade of people trying to prove this. And they couldn't. But at least the meaning of these numbers could be understood. This is Raghavendra's famous result, that this unique games conjecture controls completely these numbers. There's a very natural semi-definite program you can associate to any one of these numbers or to any CSP. And the value this algorithm, this single algorithm, gives you is the optimal value unless p equals np, assuming this conjecture. So we know exactly where these numbers arise from and for any constraint satisfaction problem. That's a major result. In fact, it sort of stands in contrast to the idea that we have to develop different problems deserve different algorithms. Sort of an amazing understanding. And we understood that, but I want to stress, well, of course, we needed to make progress. I won't even go into this isoperimetric inequalities and analysis tools that had to go here. But I want to stress that this is still a conjecture. So we ended the last decade understanding this, but without knowing whether this conjecture is true or not. And in fact, we still don't know. But something still happened in this decade. And while we had a conjecture here, we have a theorem, the 2-to-2 conjecture that Dor talked about. And while it still doesn't completely settle this conjecture, it goes a long way. It's between epsilon 1 minus epsilon. Now we get between epsilon and half minus epsilon, hardness for linear equation. It still explains lots of numbers that we saw before, and partially explain others, and it is a theorem. And again, for this to happen, as I mentioned before, lots had to happen in the world of, for example, besides other places, high-dimensional expanders, some connections of homology and local testing, and small set expansions in various graphs, including the Grassmann graph. So that's some aspect of what happened in the theory of computation in this decade. Of course, many other things that are not related maybe to this workshop, or maybe are related to this, but we'll discover it in the next decade. So it's not clear to me what surprises are waiting for us, and what will be needed to be done in order that they happen, and what consequences they will have, and what meaning it will have, and so on. So let me conclude. Going back to the field we are studying, theory of computation, it's not clear really as it evolves what kind of field it is. We talked about mathematics and technology and natural sciences, and of course it's evolving into a social science and experimental science, philosophical science. I mean, those who know that we are studying fairness in algorithms, those who know that we are theory should and can study deep nets, and in fact, deep nets are much better than animals. You can experiment them without the Helsinki breathing down your neck. I have a son who does neurobiology, so I know. But studying the mind or consciousness, we'll have to get into all these things, and the nature of the field is studying, and there are several clear things that about it that have to be recognized, and I think have to be taught. First of all, that it's an independent field. It's an independent way of thought. It's revolutionary in its impact, and it's very young. We are just in the beginning of understanding things. We see this because we are surprised by new things every day. So besides solving all our problems, which I think we are pretty good at, and drawing great young talent all the time, which we seem to be pretty good at, it's clear that we must grow because lots and lots of areas, intellectual areas, depend on that. It makes it very hard as the field grows to stay interconnected, but on the other hand, we see, and I believe in it, that core theory must be there must be a place for all areas of the theory of computation, and they themselves are growing to stay connected with each other, to inform each other, so that such breakthroughs can happen, influencing each other. And I believe that while we do it, maybe we should do more in courses and in lectures, popular lectures, to teach and educate and disseminate the meaning and the value of results in theory, both to our students and to the public at large. Thank you. Let me say something about this. I can talk about any of them at any length, but it's about them. Noga remarked in a talk last week that he can a story about Mark Twain that about something he knows he can talk and explain fully in 15 minutes.
I want to add to the question a little more, because I'm noticing that there is a movement.
Wait, I'll answer you and then you can answer. I cannot stop a Mark Twain story in the middle. Something he fully understands, he can explain in 15 minutes. Something he understands, vaguely, maybe half of 40 minutes. And something he doesn't know anything about, he can talk forever. So I want to say about your question, one fundamental idea that was suggested by John Wheeler is what's phrased as eat from bit. So I didn't say it about Turing's model, but one fundamental aspect of it is that it's discrete. And if it's supposed to explain science, chemical, biology, physics, most explanations are continuous. They work with continuous models. Many of them do. And John Wheeler suggested that maybe it's actually digital, and we should start from the bit description of the world, and it should lead to, let's say, Maxwell's equation or Einstein's equation. And in fact, this was done. So it affects both chemistry and biology and physics. And what we see more recently is a project that Dorit is involved in, and many others in some of my colleagues at the Institute, is eat from qubit, where you want to derive, let's say, the equations of the Schrödinger equation from fundamental interactions of digital qubits instead of bits. So that the world has a digital explanation is a fundamental, challenge, let's put it like that at this point, that is becoming formal in some aspects of the sciences world and will become even more, I think, in, let's say, in quantum mechanics.
So more questions? So let's thank Avi again.